Hello. So this is lesson 4.1, exponential functions. First, we're going to define what an exponential function is. So the exponential function f with base b is defined by f of x equals b to the power of x. Or instead of the f of x, we can write y equals b to the power of x. Um, b is a positive constant other than 1. So b is greater than 0 and not equal to 1. And x is any real number. Okay, let's look at an example here. So we have the exponential function f of x equals 42.2 times 1.56 to the power of x. Models the average amount spent, f of x in dollars, at a shopping mall after x hours. What is the average amount spent to the nearest dollar after 3 hours at a shopping mall? So we're going to plug in x as 3 because it's x hours. So, and we're looking at 3 hours. So 42.2 times 1.56 to the power of 3. When we plug this in the calculator, we get 160.20876, which it rounds to the nearest dollar, $160. Okay, in this next example, we are graphing an exponential function. So what we want to do is we're going to start with a table, and we're going to, so x can be, any real number. So what we can do here is we can just choose easy numbers. So for example, -2, -1, 0, 1, and 2, familiar numbers that we've chosen before. Now we've got y is going to be 3 to the power of x. Um, so 3 to the power of -2. Remember that when we have a negative exponent, it means that we're flipping the number over. So it's going to be 1 over 3 to the power of 2, which is 1 over 9. Same thing here, 3 to the power of -1, it's just going to be 1/3. 3 to the power of 0, a reminder that any number to the power of 0 is going to equal 1. And then 3 to the power of 1 is going to be 3, and 2, not 2. 3 to the power of 2 is going to be 9. Okay, so let's sketch. No, I forgot the. So -3, -2, -1, 1, 3. Actually, we're gonna 6, 7, 8, and 9. Okay. Um, our first ordered pair is going to be -2 and 1/9. So that's somewhere right here. Our next one is -1 and 1/3. So somewhere here. 0 and 1 is the next one right here. So that is here. 1 and 3 is going to be here, and 2 and 9. So that's going to be, oops, all the way up here. Okay, so let's go ahead and sketch. Looks something like that. Okay, if we look at this exponential function, we can see that it's the domain of it is going to be all real numbers. It keeps going and going. There are no restrictions in the domain. So it's negative infinity to infinity. Now, the range, on the other hand, if we look at the y values, it consists of all positive real numbers. So it goes from 0 to infinity. And notice that it does not touch 0. It gets closer and closer to it, but it will not touch it or cross it. So 0 has to be inside parentheses. Um, there's one point that every single graph of exponential function passes through that point. And that is going to be this point right here. So 0, 1. And that is because it does not matter what exponential function it is, what the base number is. Any number to the power of 0 is going to equal 1. Now, b is not going to be 0. So the y-intercept is always 1. There is no x-intercept. And notice that we are talking about the base, the parent function, b to the power of x. We haven't done any transformations to this. So that's when this thing changes. It's the parent function that is like this. Okay, next one. If b is greater than 1, so our base is greater than 1, f of x equals b to the power of x has a graph that goes up to the right and is an increasing function. The greater the value b, the steeper the increase. So if we look at this, our b here is 3. That is greater than 1. So it goes up and increases, up to the right, and it increases. Now, if b is between 0 and 1, f of x equals b to the power of x has a graph that goes down to the right and is a decreasing function. So it looks sort of like this, where the increasing goes like this. And the smaller the value of b, so the smaller the base, the steeper the decrease. Okay, next we have f of x equals b to the power of x is 1 to 1 and has an inverse that is a function. Now, 1 to 1 means that, well, it has an inverse and it, okay. It passes the vertical and the horizontal line test. So both the function itself and the inverse is a function. So for example, if I, do the horizontal line test and the vertical line test, this function passes both of them because it only touches the vertical and horizontal lines in one spot. For example, if we do a quadratic function like this passes the vertical line test. It is a function, but its inverse is not a function because it it doesn't pass the horizontal line test. It crosses the same horizontal line twice. So an exponential function is a one-to-one and has an inverse that is a function. Okay, the graph of f of x equals b to the power of x approaches but does not touch the x-axis. There is the x-axis, or y equals 0, is a horizontal asymptote. Okay, let's put all this together in a, I'm gonna sketch it right here. So I'm gonna do the y and the x-axis. Um, so if we look at number 2, it always passes the point 0, 1. So that's a point that it always passes. Now, if b is greater than 1, it goes up and increases. So this is b is greater than, I'm sorry, b is greater than, yes, b is greater than 1 here. If b is between 0 and 1, it decreases. Oops, that's not. So this is 0 to b to 1. And then the x-axis, y equals 0, is the horizontal asymptote. Okay, now transformations. Very similar to what we've done with transformations of all the other equations as well. So we're going to go ahead and start with the vertical. And that is, we're going to have a g of x equals b to the power of x plus c, which means that this shifts f of x upward c units. If we have g of x equals b to the power of x minus c, this shifts f of x downward c units. And I forgot to mention that here's our f of x. So f of x equals b to the power of x. Okay, let's look at horizontal transformation. So horizontal is the one that is done with the x. Vertical is, because it's y, it's done to the y. So that's why we're shifting up and down. We're adding it to the b to the power of x. Horizontal will be added to the x, so x plus c in um, on the exponent. That's what I was trying to say. So shifts f of x left c units. And remember that we're doing it kind of backwards as well. So even though it's x plus c, we are shifting it left. If g of x is b to the power of x minus c, then this shifts f of x right c units. Okay, next transformation is the reflection. So if it is g of x equals negative b to the power of x, this reflects f of x about the x-axis. If g of x is b to the power of negative x, it reflects f of x about the y-axis. Okay, next is the vertical stretch or shrink, When we're talking about vertical, it means that we're doing it to the y, so the c is going to be in front of it, in front of the f of x. So c times b to the power of x. So vertically stretches f of x if c is greater than 1 and shrinks if c is between 0 and 1. Horizontal stretch or shrink, it's horizontal, so we are multiplying the x by the c. And horizontally stretches f of x if x is or c is between 0 and 1 and shrinks if c is greater than 1. Okay, so let's look at an example, a transformation example. So we already graphed the graph f of x equals 3 to the power of x right here. So basically, I'm going to go ahead and copy this one from here. We need a coordinate plane. -1, -2, -3, 1, 2, 3, 4, -1, -2, 1, 2, 3, 4, 5, 6. I have to remember that we need to go all the way up to 9. There we go. Okay, so our points were for this one, it goes through 0, 1. Then we had 1 and 3. My coordinate plane is a little bit funky, not straight. And then we had 2 and 9. So 2 and 9, 1, 3, 0, 1, and then it kept coming down here. That was 1/3 and 1/9. And it gets closer and closer. So this is our parent function right here. So this one is f of x equals 3 to the power of x. Okay, so what we're going to do is we have f of x equals 3 to the power of x minus 1. So it's the minus 1 is with the x. So what we are doing is the horizontal shift. And since it is a negative, we're going to the opposite side. So we are shifting to the right 1 unit. So what we're actually doing is we're adding 1 to each x coordinate. So for example, our 0, 1 is going to be 0.11. 1, 3 is going to be 2, 3. And 2, 9 is going to be 3, 9 because we're adding 1. And here, the -1 and 1/3 is going to be 0 and 1/3, and then we're coming down again. So this is what the transformation looks like. So this one is the f of x equals 3 to the power of x minus 1. Now, even though it's not on here, let's look at what happens if it's f of x equals 3 to the power of x minus 1. So the minus 1 is not with the x, it's with the 3 of x. So this means that we are shifting down 1 unit. So we are subtracting 1 from each y coordinate. So again, we're using the parent function, the 3 to the power of x, and shifting down 1. So we have the point 0, 0. 1, 3 becomes the point 1, 2. X coordinate doesn't change, it's the y. And 2, 9 becomes 2, 8. So it looks something like this. Now, the question is, so this is f of x equals 3 to the power of x minus 1. If we look at the first two, so the f of x equals 3 to the power of x, we know that y equals 0 is our horizontal asymptote. The same thing for the y equals 3 to the power of x minus 1 is a horizontal asymptote. And I can't remember if I mentioned this before. Asymptotes are with a dashed line because it's not a, like it's if you, for example, do Desmos or try it with Desmos, you won't see the actual line. We don't want to mistake it for the actual graph. So that's why we use the dotted line for the asymptotes. So both of those have the horizontal asymptote as y equals 0. Now, for the f of x equals 3 to the power of x minus 1, we shifted it down 1. So that means that the asymptote shifts down 1 as well. So our horizontal asymptote is y equals negative 1 now. If we had shifted it up, the asymptote would shift up also. Okay, next we're going to look at what's called the natural base. So the number e is defined as the value that 1 plus 1 over n to the power of n approaches as n gets larger and larger. So as n approaches infinity, the approximate value of e to 9 places looks like this. You will find e on your calculator. There is on the left side, there's an ln button, and on the top, like above it, is e to the power of x. So you're going to use the second and ln to get, if you press on your calculator second and ln and then 1, you get this number right here. So it's the second ln button and then 1, and then you press enter. So this irrational number e, it's just like pi. We know that pi is an irrational number. It never ends. E is a similar one. So we use the, or we approximate it to 2.72. It is called the natural base. So the function f of x equals e to the power of x is called the natural exponential function. Okay, let's look at an example. The gray wolf population is modeled by the function f of x equals 1,144 times e to the power of 0.0325x. So, hold on. Models the gray wolf population of the Western Great Lakes. F of x years after 1978. Project the gray wolf's population in the recovery area in 2014. So 1978 and 2014, we need to calculate what our x is. 2014 minus 1978 is going to be 36. So we're going to plug in 36 where the x is and do 1144 times e to the power of 0.025 times 36. Now, when you plug this in the calculator, what you need to do is make sure that when you're putting it in the calculator, either um, it stays on like as the exponent because this whole thing is the exponent, or you might need to use parentheses here so that the calculator doesn't think that only the 0.032 is an exponent and then you multiply the whole thing by 36. But your answer should be 3,686. So the projected amount of gray wolves in 2014 is um, 3,686. And you can tell how, we're talking about 2014. We're already 11 years past that. Okay, next, where we use the natural base or actually not, yes, the natural base and overall exponential functions are compound interest. So we have um, T is the years, A is the balance, P is the principal, so the initial deposit, and R is annual interest rate in decimals. So for n compounding periods per year, our formula is A equals P parentheses open 1 plus R over N close parentheses N times T. For continuous compounding, A equals the principal times the natural base E to the power of RT. Okay, let's look at an example. We have a sum of $10,000 is invested at an annual rate of 1.08%. Find the balance in the account after 5 years subject to quarterly compounding. Okay. So what do we know here? We know that our principal is $10,000 because that is what is invested. Our annual rate is 1.08%. Now, we need to convert that to a decimal. Percents to decimals, we divide by 100. So we move the decimal 2 to the right. We get 0.0108. Time is 5 years. That was the rate, and that's the, and then quarterly compounding. The one thing that this is, N is how many times compounded per year. So our N here, we have quarterly compounding. So there's 4 quarters in a year. So N equals 4. Now we are plugging it into this formula right here because we have the quarterly compounding. So A equals $10,000 parentheses 1 plus R is 0.0108 divided by N, which is the 4, and then to the power of 4 times 5. Again, make sure that if you're plugging this whole thing in the calculator, that this is inside parentheses. So our balance is going to be $10,554.08. Okay, next example, we have the exact same amount. Our principal is still $10,000. Oops. Annual rate is the exact same. So 0.0108 as a decimal. Years is 5. And now we are continuously compounding. So we are using this one right here. A equals P times E R to the power of T. So our principal is $10,000. E to the power of rate 0.0108 times the years, which is 5. So when we plug this in the calculator, we get $10,554.85. Very close to each other, but this one is greater than this one right here. Okay, that's it for lesson 4.1. Let me know if you have any questions. Bye.